In this video, we will build an MCP server that allows Claude Desktop app to search images stored on your computer using natural language. This project is an extension of one of my previous videos where we built an AI-powered image search engine using OpenCLIP and FAISS. Today, we will take that project one step further by creating an MCP server and connecting it to the Claude Desktop app. Once it is connected, Claude will be able to search images stored on your local computer using natural language. It can find matching images and even open them in your default image viewer. Before we start building it, let's first see how the final application works. Let's start by asking Claude, find images in a restaurant. Claude calls our MCP server, searches the local image collection, and returns the matching result. It then asks whether I want to open the image. I will reply yes. As you can see, the image opens in the default image viewer on my computer. Now let's try another query. Find images with friends going on a trip. Again, Claude searches the indexed images and returns the most relevant matches. Let's open a few of these images. Now let's try something different. Open a beachside photo. Claude understands the request, finds the matching image and opens it. So with this MCP server, you can search images stored in a specific folder using simple natural language. And you can even open the matching images directly from Claude. So these are the sections we will cover in this video. Before we begin, I highly recommend watching my previous video on the multimodal image search engine, since we are going to reuse that project in this tutorial. In this video, we will reuse the text search functionality from that project, expose it as a MCP tool, and build an MCP server that Claude can use to search images on your local computer. Now you might be wondering, how does the application know which image to return and where that image is stored? For that, we first need to create an index of all these images. We use FAISS, which is a vector database designed for fast similarity search. During the indexing process, each image is converted into a vector embedding using the OpenCLIP model. These embeddings are then stored in the FAISS index.bin file. At the same time, we save the corresponding image path in the image path.pkl file. Later, when a user searches for an image, the application searches the FAISS index to find the most similar embeddings. Using the matching index, it retrieves the correct image path from the image path.pkl file. So before we can search images, the first step is to generate these vector embeddings and save them in these files. To do that, we will use this Python script called buildIndex.py, which scans the image folder, create the embeddings, and build the search index. Let's go through the indexing script step by step. First, we need to specify the folder that contains the images we want to index. Folder path. In my case, all the images are stored inside this folder. You can replace this with the path to your image folder. This code checks whether your computer has an NVIDIA GPU with CUDA support. We automatically choose the GPU if one is available. Otherwise, the application falls back to the CPU. The code works in both cases, but indexing is much faster on GPU. Next, we load the OpenCLIP model. This code loads the OpenCLIP AI model into our application. The model is responsible for converting both images and text into vector embeddings, which we use later for similarity search. The first parameter is VITB32, VIT stands for Vision Transformer, which is an AI model designed to understand images. Next is pre-trained weight. This tells OpenCLIP which pre-trained weights to load. Along with the model, OpenCLIP also provides a pre-processing function. Images can have different sizes, resolutions, formats. However, the model expects every image to be in a consistent format. The preprocess function automatically prepares each image by resizing it, cropping it, and then converting into tenses that the model can understand. Finally, we move the model to the selected device. Next, we create two empty lists, embedding and image path. The embedding list will store the vector embedding generated for each image. The image path list will store the location of each image on your computer. Later, when we search for an image, these two lists work together. The embedding helps us finding the matching image, and the corresponding path tells us exactly where that image is stored. Next, we go through every file inside the image folder one by one. We only want to process image files, so we first check whether the file is a JPEG, JPG or PNG image. Any other file types are skipped. Here we create the complete path to the image file. Next, we load and prepare the image. First, we open the image and convert into RGB format. Then we pass into the preprocess function. As we discussed earlier, the function automatically resizes, formats and normalizes the image so it matches the format expected by the OpenCLIP model. Next, we use unskews to add a batch dimension. Even though we are processing just one image, the AI model expects its inputs to be in the form of a batch. So this converts the image from a single image into a batch containing one image. Finally, we move the image to the selected device so the model can process it. The OpenCLIP model converts the image into vector embedding. Similar images produce similar embeddings. You will also notice that we use torch.noGrade since we are only using the model to make predictions and not training it. This tells PyTorch not to calculate gradient. As a result, the code uses less memory and runs faster. Normalization makes all embeddings the same length, making image comparisons more accurate. Next, we save the embedding. Here we move the embedding from the GPU to the CPU if necessary, convert it into a NumPy array and store it in the embedding list. Finally, we save the image path. This stores the location of the image in the separate list. Until now, all the embeddings were stored in a regular Python list. Here, we convert that list into NumPy array because FAISS works with NumPy arrays, not with Python list. Next, we create the FAISS index. Think of FAISS index as a search engine for vectors. Instead of comparing the query with every image one by one, FAISS organizes the embedding so it can quickly find the most similar ones. Now we add all the image embedding to the index. At this point, the FAISS index contains the embeddings for every image in our collection, making them ready for fast searching. Building the index can take some time, especially when you have thousands of images. So instead of rebuilding it every time, we save it to a file. This creates a file named faissindex.bin, which stores all the vector embeddings. Next, we save the image path. This creates another file called imagepaths.pkl. This file stores the location of every image on your computer. Let's move on to the second part of this project, setting up the MCP server. For that, I have created a new file called image search mcp.py. This file acts as the bridge between our image search application and the Claude Desktop app. This code sets up logging for our application. Instead of using print statements, we will use logger to display messages about what is happening inside the application. Since an MCP server communicates with Claude through standard input and output, we should never use print statements. Instead, we configure logging so that all the messages are written to the error stream without interfering with the communication. The first step is to create the MCP server. This line creates an MCP server named Image Search Server. You can think of it as creating a server that allows Claude Desktop to communicate with our Python application. Next, we define a few configuration values. These variables store the configuration used by our application. For example, index file and image path point to the files we created earlier using the build index script. The path must be the full file path like this. Also make sure to use double backslashes in the path. Since this is a Python string on Windows, using double backslashes ensures the path is interpreted correctly. We also specify the OpenCLIP model that we will use for generating text embeddings during search. Top K controls how many matching images FAISS should return, and threshold defines the minimum similarity score required for an image to be included in the result. This line loads the OpenCLIP model, which is the AI model responsible for converting text into vector embeddings. Since our image embeddings were generated using the same model while building the FAISS index, we must load the exact same model in the MCP server. Otherwise, the text embeddings would not match the stored image embeddings. Tokenizer. A tokenizer's job is to convert the user's text into a format that the AI model can understand. For example, if the user searches for sunset beach, the tokenizer breaks this text into small pieces called tokens. Then these tokens are passed to the OpenCLIP model to generate a text embedding. This function loads the previously created FAISS index and the image path into memory. As soon as the MCP server launches, it automatically loads the FAISS index and image path, so it's immediately ready to search images. Now let's look at the search function. This function is responsible for searching our image collection using a natural language query. The first step is tokenization. The tokenizer prepares the user's text for the OpenCLIP model. Next, the OpenCLIP model converts the tokens into a text embeddings. Just like images have embeddings, text also has embeddings. After generating the embeddings, we normalize it. Next comes the actual search. We pass the text embeddings to the FAISS index. FAISS compares it with all the image embeddings stored in the index and returns two values. The first is scores, which tells how similar each image is to the search query. The second is IDs, which tells us the position of the matching images in the FAISS index. We will filter out low scoring matches and keep only the images that are similar enough to the user's query. Finally, for each matching image, we create a result containing the file name and the image path. These results are then returned to the MCP tool, which later sends them back to Claude for display. Search images. This creates a tool named Search Images. It accepts one input, query, the text the user wants to search for. Next, the description. This is the description of the tool. It tells Claude what the tool does, when it should be used, and what kind of input it expects. Because of this description, Claude knows when to use this. For example, if a user says, "Show me beach photos" or "Find images of cats," it should call the Search Images tool automatically. Basically, in this MCP tool, we call the search function, which returns the images. Open Image function. This creates a tool called OpenImage. It accepts one input, which is the path. If the user says open the first image, Claude knows it should call this tool with that image. In this line, it opens the image using the default image viewer on Windows. MCP.run. This line starts the MCP server. Once the server starts, it waits for request from Claude. Claude can discover all the tools registered with mcp.tool. When the user asks something like "Find images of sunset beach," Claude sends the request to the server. The server runs the appropriate tool and sends the result back. Now let's set up the application. The first step is to clone the GitHub repository to your local machine. I have shared the repository link in the description below. Once you have cloned it, open the terminal and navigate to the project folder. Next, we will create a Python virtual environment. A virtual environment is an isolated workspace for your project. It keeps all the required Python libraries separate from the other projects, which help you to avoid version conflicts. I highly recommend using a virtual environment for this project. After creating it, activate the virtual environment. Once it is activated, install all the required libraries using the requirements.txt file. Now we are ready to configure the MCP server. The next step is to create the vector embeddings for your images and save them in a FAISS index. To do that, run the build-index.py script. Before running it, update the folder path variable with the path to the folder that contains your images. Keep in mind that the application can only search images that are inside this folder, because only those images will be indexed. Once you have updated the folder path, run the script. The script will go through all the images, generate vector embeddings using OpenCLIP, and save the result as FAISS index.bin and imagepath.pkl. When the process finishes, you will see a message showing how many images were indexed. Now add the index file path and the image path in image_search_mcp.py file and save the file. Now it's time to connect our MCP server to the Claude Desktop app. So install Claude Desktop on your computer. I already have it installed. So let's add our MCP server. Open Claude Desktop and go to File, Settings, Developer section. Here you will see the local MCP server section. Click the Edit Config. This opens Claude's MCP configuration file called cloud_desktop_config.json. Inside this MCP server section, add the configuration of our server. This configuration tells Claude Desktop how to start our MCP server whenever Claude needs to use it. This section contains the list of MCP servers that Claude can use. You can register one server or multiple servers here. Next, we need to add our MCP server. This is simply the name of our MCP server. You can use any name you like. Next is the command line field. This tells Claude which Python interpreter it should use to start the MCP server. In this example, we are using the Python executable from our virtual environment. Using the virtual environment ensures that the server runs with the correct versions of all the required libraries. To get this path on your own system, open the terminal in your project folder and activate our virtual environment. Then run this command. This prints the full path of the Python interpreter that is currently being used. Simply copy that path and paste it into the command field. One important thing to remember is the double backslashes. Since this is a JSON file, a single backslash is treated as an XCAP character. That's why Windows path must be use double backslashes, otherwise the configuration will be invalid. After that, update the argument section with full path to your image_search_mcp.py file. To get the file path, open the file in the code editor and copy the path. Once you have saved the configuration file, we are ready to start the MCP server from Claude Desktop. So that's it. Our MCP server is now configured. The final step is to restart the Claude Desktop app. Sometimes simply closing and reopening Claude is not enough because the application may still be running in the background. So open the Task Manager and end all the Claude processes. Then launch Claude Desktop again. Go to File, Settings, Developer section. If everything has been configured correctly, you will see that our Image Search MCP server is up and running. Now it's time to test it. Go back to the chat window and enter a query such as show me images of a sunset beach and other queries that you like. One important thing to remember is that adding an MCP server doesn't guarantee Claude will use it for every request. Claude decides whether a tool is needed based on the user's prompt and the tool descriptions. Sometimes it may answer from its own knowledge instead of calling your MCP server. If that happens, you may simply be more specific. For example, you can say use a local image search MCP server to find sunset beach images, or search my local images using the MCP server using search images tool, etc. These prompts may invoke your MCP server. And that's it for today's video. I hope this tutorial helped you to understand how to build an MCP server in Python and connect it to Claude Desktop app. If you found this video useful, please give it a like and subscribe to the channel. Thank you for watching, and I will see you in the next video.